Hello everyone, welcome to the channel. Today's topic is deep learning and neural networks. Can we call deep learning and neural networks as second brain, as these networks are designed to mimic the neurons and neural networks of superbrain, that is human brain. In this video, we'll try to understand the problems with machine learning models, why we need deep learning, how to choose machine learning over deep learning and vice versa. Then we'll cover neural networks and transformer models in detail. Let us quickly go through machine learning pipeline and understand the problems in machine learning. Machine learning is a set of algorithms used by machines like computers, to learn from raw data to predict unknown data. Machine learning is data driven. Now, coming to the machine learning pipeline, the first step in machine learning is define the problem statement. Like identify a car in an image, then collect relevant data which contains the car in the image, then data labeling, then comes the feature engineering or featureization where features are extracted and raw data is converted to machine learning number format. Then train model by applying rules to known data to predict unknown data. Then evaluate the model and then deploy the model. If model performs well, then retain the model, otherwise retrain the model. The entire flow starting from defining problem statement to model deployment is almost same for machine learning and also for deep learning except for the featureization or feature engineering step. Let us focus on this step, feature engineering. What is feature engineering? As computers understand only numbers, the feature engineering or featureization converts raw data or string data into numerical data. Where does the data come from? The raw data could be iris data, IMDb data, data from internet. This data is translated into numbers and then converted into matrix form and vectors. The machine learning processes this data in rows and columns by applying mathematical equations. Let us understand feature engineering with an example. In computer vision, to detect objects in an image or to classify the images, computer vision uses features. Features are edges, corners, boundaries of images, textures, patterns of pixels and images. If we are trying to identify the vehicles in an image, then features would be wheels, two-wheeler or four-wheeler, size of the vehicle, number of seats in the vehicle, shape of the vehicle. What are the features in text? Text contains words, so features in the text takes form of count. In natural language processing, NLP, which is used for text processing, words are discrete items. So feature takes the form of counts. Let's say we are analyzing the sentiment of a document or analyzing the sentiment of customer review comments for a service. If the words like happy appears in the document, then feature count is set to 1, else set to 0. If sentiment of the document is decided by the words like happy, like, smiley symbols, or sad, unhappy, if happy or like or similar words appear, then more count to these words. Then the sentiment of the document is classified as positive sentiment. Let's say word happy appears 50 times, word like appears 30 times. As the total word count of positive sentiment is 80, the customer is happy with the service. If we are trying to predict the price of the house, then features would be size of the house in square feet, number of balconies, number of rooms inside the house, price of the house, and the location of the house, that is locality. The choice of the features is crucial to the success of machine learning algorithms. So, how are these features extracted? The features are identified and extracted from raw data manually and labeled manually or by using labeling tools with human intervention. Data scientists manually label the data and select the features. The manual feature engineering process works well for small data set but not for large data set. Handcrafting features on small data produces high accuracy but less accurate with complex and unstructured large data set. Handcrafting features needs continuous human intervention and takes lot of time to produce highly accurate models on large data set. So what is the solution to the low speed accuracy issues of machine learning while processing unstructured large data sets? Solution is we need a system that can learn the data patterns automatically from large unstructured data sets without human intervention. We need a system that can learn from complex data sets to simulate human brain, human cognition. How do we achieve this? Automatic feature extraction. This is achieved through deep learning. In deep learning, which is a subset of machine learning and AI, feature engineering is simplified with only basic set of features as system learns on its own by processing the data in layers. As we saw in previous slide, feature extraction is a manual process in machine learning, works well on small data sets. Structured and semi-structured data sets like images with labels or data in table form, rows and columns like spreadsheets. As the feature extraction process is manual, the machine learning system takes time to learn the patterns in the data. Machine learning models needs less computations and provides good accuracy for small data sets. Deep learning can process complex large unstructured data sets in layers. Patterns in data are learned automatically with minimal or no human intervention or guidance. Deep learning learns by itself without much guidance from software programmer. Deep learning produces highly accurate results on large data set. As the data is processed in multiple layers and the data is set as large, deep learning is computationally expensive. So when to choose machine learning and when to choose deep learning? Use machine learning if you are developing simple applications like spam filtering to filter emails into spam and not spam. Machine learning improves with time. So machine learning can be used in systems like Netflix applications suggesting your favorite movie. The system learns about your favorite movie over the time. Use deep learning if you are developing complex applications in healthcare to detect cancer cells. Use deep learning if you are developing AI based voice assistants or AI agents or image recognition in computer vision. Advertisements are served to you using search history. Uses deep learning. There is no hard and fast rule to use machine learning or deep learning. There can be trade offs. In case a simple linear model using machine learning is not producing accurate results, then try deep learning. Trade off effort against the accuracy. Simpler models, if they don't achieve the accuracy you need, then use DL. Otherwise, use ML. Before moving to the next slide on deep learning, let us quickly look into artificial intelligence. AI is a superset of machine learning and deep learning. AI mimics human brain. Use simple rule-based AI for AI chatbots for customer services. Use advanced AI for gaming applications and predictive analysis. Moving on to the next slide. What is deep learning and neural networks? Deep learning is a branch of machine learning inspired by structure of our brain and how computations are performed in human brain. So we can call AI models based on deep learning models second brain. Deep learning algorithms find patterns in the data and then use those patterns to make predictions about new data. Deep learning does automatic feature engineering or feature extraction, which we already saw in previous slide. Let us understand deep learning in deep. Moving to the next slide. Deep learning mimics human brain. So there are neurons in the human brain. Deep learning is similar to neurons in human brain. Neurons are cells that communicate with other neurons and form network. Similarly, how neurons are organized in layers in human brain, neurons in neural network are organized in layers as well. In neural network, there is something called perceptron, which is considered as an artificial neuron. Neural network is defined by number of neurons, number of layers, and type of connection between the layers, whether it is a forward connection or a backward connection, as shown on the image. How do we decide on number of hidden layers? Based on the application and the number of features which you want to extract, you can decide on the number of hidden layers. More hidden layers may increase the computational process. How does neural network learn? Neural network learns by updating the weights W1 and W2. Each input x1 is assigned a weight W1, input x2 is assigned a weight W2. As the data moves to the network, the neural network learns the patterns in the data by adjusting these weights W1 and W2. As the data moves to the network, the data is influenced by the weights and the activation function type. For details on what is activation function, please watch the video on Machine Learning Basic Concepts Part 1 and Part 2. I have provided the link for that video in this video description. Let us understand neural network with examples. Let's say you are using Face ID to unlock your mobile phone. When setting up your phone, you train the algorithm by scanning your face. Each time you unlock your phone using Face ID, the camera on the phone captures hundreds of data points which create a depth map of your face. The mobile phone, has inbuilt neural network engine. This neural network engine will perform the analysis to predict whether it is you or someone else trying to unlock the phone. Moving on to the next slide, let us look into neural network architectures CNN, that is Convolution Neural Network, RNN, Recurrent Neural Network, and the latest updates in neural network, that is transformers, and LLMs and LVMs, large language models and large visual models use these transformers in computer vision and NLP applications. Let us look into CNN, that is Convolution Neural Network Architecture. In CNN, the network automatically learns features in the data via convolution. Due to convolution layer, CNN scales well with the images, so it is used in image classification, object detection, and tracking. Let us look into how CNN works. CNN consists of three layers. Input layer that captures the height, width, and depth of the images. As you know, the images are made of RGB pixels. The depth represents these color channels. Then convolution layer to extract features of images like edges, corners, textures. These feature extraction layers are also called as learning layers. Convolution is mathematical operation on how to merge the two sets of information. Take input, apply convolution, and give features as output, which in turn is input to the next convolution layer. Convolution, then activation function, then we have pooling. Then again we have convolution, activation, pooling. This gets repeated till we have good number of features. Activation function that is used in CNN is ReLU, that is rectified linear unit. Activation function classifies input information as useful and not useful and carry forwards useful information and reduce noise. So what is the role of activation function in this entire CNN architecture? It takes the useful information forward and it drops the information that is not useful. If our problem statement is to find the input image has ball or not, then the ball details are carried forward by our brain. When the image is fed to the brain, the two images fed to the brain tries to classify the information into two categories, useful information and not useful information. As our goal in CNN is to identify whether a ball is present in the image, we focus only on the ball, useful information. Similar to brain, the neural network carry forwards the ball details to next layer and rest of the details in the image are considered as noise. The activation function ReLU is nothing but a kind of absolute function which we use in our mathematics, or you can even call it as a rounding function. It is not exactly rounding or absolute, but you can understand it as a rounding or absolute function. It clips the values between 0 and max. Let's say the result is 0. Then ReLU accepts it as 0. If the result is negative, minus 5, then ReLU clips that minus 5 to 0. If the value is set to 5, then ReLU takes it as 5 because 5 is greater than 0. Then let us look into the pooling layer. Pooling layer uses filters and downsample the image, thereby reduce the data representation progressively over the network to control bias or overfitting. Pooling layer keeps only important features of the image so that the image size reduces as the network process progress. Let's say if the input image size is 30 by 32 by 32. If the pooling layer is set to 2 by 2 filter, then the output image would be half of 32 by 32, that is 16 by 16. We will not lose any information due to this downsampling of the images as we retain the important information by convolution. Convolution layers and pooling layers are repeated number of times. in a sequence to find the features automatically as opposed to machine learning handcraft manual feature extraction. In final output layer, features are combined for classification to produce scores or probabilities. CNN scales well with images, so it is used in computer vision. Now let us look into the next neural network architecture, the most popular architecture, that is RNN. Recurrent neural network process input sequentially, one token at a time, preserving the text order with feedback loop. RNN focuses on modeling the temporal relationship between the data. RNN has three layers: input layer, hidden layer, and output layer. Hidden layers can be more than one. In RNN, we can take input from previous step into neuron as part of incoming information, this arrow, and sends this information to the next hidden layer. For example, sentiment analysis of customer review comments with words happy, sad, like, dislike, which we saw in previous slide. This sentiment analysis takes multiple words from the customer review comments and output signal one that is customer review is positive or negative. There could be many scenarios, many to many or one to many. Like image captioning takes image and output sequence of words. RNN can retain the long sequences, hence it is used in natural language processing. In previous slide we saw how CNN is used in object detection and RNN for understanding text sequence. Are there any drawbacks with CNN and RNN? Are there better neural network architectures than CNN and RNN? The answer is yes. The latest development in neural networks is transformers. Recurrent neural network learns in sequence. RNNs were used for text processing due to their ability to process sequential data. For sequential understanding, RNNs maintain internal state that retains information from previous words. RNNs are good at processing long sequence text, but encounter challenges with long range dependencies in long sequence. RNNs try to retain old information, but they forget old information. This is because error function or the loss function called vanishing gradient descent. If you are curious to know the technical details of vanishing gradient descent and how the gradient vanishes, then please watch my video on machine learning concepts. I have provided the links in this video description. So in simple terms, the vanishing gradient descent, which is error function or loss function in neural network, reduces the weights that are propagated back to improve the prediction. The weights become smaller due to the derivatives of gradient descent applied using mathematical equation. So what happens when weights become smaller? The early inputs changes little. Like hidden layer 1, when it is back propagated, the inputs when applied by mathematical equations like gradient descent become smaller, and these smaller input changes are passed to the hidden layer, and again the changes are back propagated. So as the network moves on, the input changes at the early stage becomes small, hindering the network's ability to learn and remember long-term dependencies within the data. How do we fix these problems associated with RNN sequential capabilities in remembering long-term dependencies? The solution is using forward network based models called transformers. Unlike RNN, which struggle with finding dependencies of words in sequence, transformer models find the relationship between all words in the long sequence, no matter how far apart dependencies are. Transformers does not have built-in sequential processing capabilities. How do transformers remember the words in long sequences? How does transformer remember the context in long sequence? Transformer remembers the long sequence dependencies in a sequence by three important techniques: the embeddings, positional encoding, and self attestation mechanisms. Let us understand the word embeddings. Embeddings enables the model to capture the different aspects of the word. Different aspects means different meaning of the word. For example, when I say I'm at bank, the first thing that comes to your mind is financial institute to deposit money. When I say I'm at river bank, that means I'm on vacation. The meaning of bank is different in both the sentences. Let's look at two more sentences. What is stock price? Do we have sufficient stock of LPG? In the first sentence, the stock price refers to equity shareholders. In the second sentence, sufficient stock means inventory. So, embeddings capture the different aspects of the word bank stock in example sentences. Embeddings are large list of numbers representing different aspects of the words being embedded. The model learns these synonyms and context during the training process. Then comes the positional encoding. Positional encoding maintains the order of words within a sequence. Positional encoding gives the relative and absolute position of the word within a sequence to understand the context and meaning of a sentence. The position is calculated based on sinusoidal functions. Understanding the mathematics is not necessary at this point. There are APIs and modules to perform this mathematics like transformers, tokenizer, positional embeddings. We can just call those APIs and modules while writing the software code. Let us look at these sentences for positional encoding. A fast moving car jumped red signal. It was a red car. Without positional encoding, the transformer model would not differentiate between the fast moving car in the first sentence, then the word it in the second sentence, which refers to fast moving car in the first sentence. The word red in the first sentence refers to traffic signal or traffic light. The word red in the second sentence refers to the color of the car. Next topic in transformers is self-attention. Self-attention mechanism allows the model to dynamically weight the importance of each word in a sentence relative to every other word. In the previous example, the word it in the second sentence would be mapped to the fast moving car in the first sentence with weights. Transformers represented as encoders and decoders architecture. Encoders understand input sequence context. Decoders predict the next word. Input sequence is converted to embeddings and then processed by encoder, which uses self-attestation mechanism. Feed forward networks and then the decoder decodes the sequence and produces output probabilities. Position wise feed forward networks. In this feed forward network, input moves in one direction, that is, from input layer to hidden layer to output. In feed forward network, there is no backward propagation like RNN. In general, transformers consist of encoders, decoders, but there are also encoder only models like BERT, bidirectional encoder representations from transformers, and decoder only models like GPT models. The computations required to learn token words representation can be parallel using graphic processing units. This parallel processing makes it possible to use large amount of textual data to learn token representation. This parallel processing reduces model training cost. So which neural network is used in computer vision and natural language processing? Computer vision enables machines to understand visual information from the pictures, images, live camera feeds. Computer vision teaches machines to see and make decisions based on visual input. Natural language processing NLP enables machines to understand text information from human languages. NLP teaches machines to understand language, spoken words, or text messages and make decisions based on text input. So, which neural network is used in computer vision and NLP? Is it CNN or RNN or transformer architecture? If you are using ChatGPT application which is based on natural language processing, then the answer is clear. The natural the neural network architecture used in NLP is transformer architecture because the T character in GPT stands for transformer. GPT stands for generative pre-trained transformer. If you are building a small simple AI chat application with yes or no kind of short replies without a long sequence dependency in a chat conversation, then you can still use RNN. Otherwise, for large AI chatbot applications which use large language models like LLMs, then transformer models produce better results. So that is about text. Then how about images? Computer vision application like image classification or object detection. Which is better for images? CNN due to convolution or transformer model. Large language models LLMs are used for text. There are vision language models or large vision models LVMs for visuals. LVMs perform image captioning. In LVM's architecture, an image encoder is used to extract visual features followed by language model that generates a text sequence. The image encoder could use a transformer model architecture like Vision Transformers VIT. As in large language models LLMs in text we have text tokens. Similarly in large vision models we have picture tokens. The pictures or images are segmented into smaller image tokens and fed to the transformer encoder for processing. There are also LMM, that is large multi-models which process different types of modalities like text, image, audio, video using transformer based architecture. So, which network is better? RNN is better for processing long sequences but encounter challenges with long range dependencies. What are these long range dependencies? Let us understand this with an example. Let's say A car jumped the red signal. The car is red in color. It has four people. It it went and hit a bus. So I have used it twice in the sentences. As the paragraph or the sentences becomes complex, the reference to the it word is a dependency which becomes complex to understand for RNN because the it is far away from the actual word car. These kind of distance or the distance is very well understood by transformer models. So if there is a big gap between the actual word and the it references, then better to use transformers. As of today, still CNN is better for computer vision than transformers. Finally, choose RNN or CNN or transformer models based on your application needs, time to develop the application, choose a neural network which is cost effective and time efficient. If you have any questions, please let me know. Please subscribe to the channel. See you in the next video. Until then, thank you for watching and happy learning.